I want to share some more algorithmic composition devices and techniques with you, starting with serialism. I hate to collapse serialism into a very brief, even part of a lecture, but we'll try to extract some of the key ideas. And I just want you to be aware that serialism it refers to an entire genre, maybe movement in music and music history, a number of composers, and tremendous influence. Arnold Schoenberg was the champion of serialism, and he was trying to get away from the state of affairs in music, which was very much based on harmony, fairly advanced and rich harmony, but kind of rooted in tonal centers and musical scales. And he wanted to develop a system and a theory of music that sort of denied the existence of tonality or took us away from tonality and scales. And so serialism is based on the chromatic scale, all 12 notes per octave with equal ratios between half steps. And so just some terminology. A pitch is an element of the chromatic scale. A pitch class is the pitch modulo 12. In other words, C sharp without regard to an octave. You know, there are many C sharps. There's one in every octave. And so that class of pitches called C sharp is a pitch class. A tone row, and now we're getting into serialism, a tone row is a permutation of the 12 pitch classes from C, C sharp, D, up to B. If we take a permutation of that, in other words, and just pick an order, that's called a tone row. And music based on tone rows can be atonal because every pitch in the chromatic scale is expressed in this tone row. As part of the theory of serialism, there are transformations on tone rows. So if we call the original tone row P sub I, then the transposition of that is just P sub I with some offset, but always calculated modulo 12 because we're dealing with pitch classes and not actual pitches. The inversion is essentially the negative of the original row. So all the upward intervals become downward intervals of the same size and vice versa. We can play the tone row backwards, that's called retrograde. And there's also an interesting operation where you multiply every pitch class number by 5. It maps you into a different tone row. So why serialism? Well, in general, listeners cannot hear retrograde and other inversion relationships in tone rows. However, the intervals are preserved. So if you base your music upon playing tone rows and transformations on tone rows, you get, to some extent, some structure because intervals are repeated. And somehow there's this character of different tone rows that's preserved by these intervals. Also, if you do base music on these tone rows, you're sort of guaranteed or you're forced to use every pitch in from the 12-note chromatic scale, and this sort of denial of tonality produces new sounds and new textures in music. Let's go on to another topic, which is fractals in nature. So melodic contours actually are often fractal-like. So what's a fractal? A fractal is a complex shape or curve in which the macro character of the curve is repeated at different scales within the overall form. I know that's pretty abstract, but the main point is that you can use fractal curves to generate music data, and because fractals arise in nature, we can take a lot of material from nature that has fractal like curves. So, for example, if you look at a coastline and you see little indentations in the coastline where a stream comes into the ocean, let's say, and then you see bigger indentations where maybe a river comes into the ocean, but within that river scale indentation, there are smaller scale indentations. So it's very recursive and self-similar. A coastline and the variations in shape on a coastline is can be rendered as a melody. In fact, there's a fairly famous piece by Larry Austin called Canadian Coastline. Another mapping of sort of nature into music, although I think not actually with a fractal, is John Cage's Atlas Eclipticalis. So this is a very interesting algorithmic composition technique. Take forms and shapes from nature and map them into sound and melody. Another thing we can do is use grammars. So what's a grammar? In computer science, grammars are used to describe, formal grammars are used to describe programming languages. In Nyquist, a function definition is the word function followed by an identifier, followed by an open paren, and followed by a list of parameters. We have grammar rules that generate legal programming expressions. We also have grammars in natural language. A sentence is a subject, is maybe a noun phrase followed by a verb phrase is one rule. So we can make grammars for music. We can say a melody is an intro and a middle and an ending. And what's a middle? It's a phrase, or maybe it's a middle, another middle, and a phrase. So this is a recursive rule. And then what's a phrase? Sequence A followed by a sequence B. We have to define what all these things mean, but this approach can lead us to introducing some recursive structures and generative structures into music. Here's an example down below of how you could translate this into a program. The rule for melody, which is a sequence intro, middle, ending, is actually just a Nyquist sequence of function calls to intro, middle, and ending. And what's a middle? Well, we pick randomly to either generate a phrase or we generate a recursive call to middle followed by a phrase. And so we can directly translate rules of grammar into functions in Nyquist that can generate some very interesting musical structure, musical form. The last thing I want to talk about now are pitch and rhythm grids. So the idea of a grid is just that the idea that we can pick continuous random numbers, shapes, maybe from nature, maybe from random number generators, and we can quantize those according to a grid, which might introduce a bit of a structure of its own. So, for example, here is a function called pitch filter that looks to see if the pitch P is a member of list F. And if it is, then we return P, so we pass through the grid. If it's not, then we add 1 to P and we run it through the filter again. So this allows us to basically put any set of pitches in as F, and we will sort of constrain or will force our input pitch P to equal one of the members of this list F, and that's the output. So here we have some functions that call on this pitch filter to to control some musical parameters, and I'll play some examples from that. So that was some tonal music. You could probably hear that it was part of a scale, and that scale was created by forcing pitches into this grid. Let's play one more. So there you could hear that we were definitely changing the grid and changing scales or changing harmony. Where do these changes come from? Well, they could be generated by hand or by a grammar or by fractal, any number of techniques, and these can all be combined in algorithmic composition. We can also quantize rhythms. So here we are going to take random times and quantize them to a beat. We do that simply by taking the time, a real value time, and divide it by some number, which is the beat length, and round that to the nearest integer. So now we have an integer number of beats, and then we multiply that back by the integer number of beats times the beat length, gets us back to the time. And so here's an example of taking random times and quantizing them to multiples of the beat, which looks like is 0.15 seconds. So we have a very interesting combination of something that sounds very random, and yet it has a very clear kind of beat-oriented metrical structure.